Now, we come to one of the most important concepts and definitions in linear algebra, and this is going to run through a lot of the theory about this subject. And I'm going to start by relating it to the systems of simultaneous equations we just looked at. And I'm going to do a little trick, and if you've seen this trick, play along, otherwise it may blow your mind a little bit. Suppose we have the following system of simultaneous equations that our algebra teacher gave us. And we're going to solve this the old-fashioned way, instead of using matrix algebra, and then we're going to relate it to that. So suppose somebody says 2x plus 3y equals 8, 4x plus 6y equals 11. Okay, so take that system of simultaneous equations, and you are tasked with finding values of x and y that will satisfy both these equations, right? Same normal thing. So I'm going to do this the way I like to do it. I'm going to say 2x plus 3y equals 8. That's our first equation, right? So let's subtract 3y from both sides, because my purpose is to get x by itself, so we can substitute it into the other thing, right? So if we subtract 3y from both sides, we get that. Divide by 2 on both sides, and we get this. And so great. So now I've got I've got y in terms of x. Excuse me, x in terms of y. So now I'm going to plug it into this thing, and I'm going to say 4 times x, but we just found out that x was equal to 8 minus 3y over 2, plus 6y equals 11. We are almost home free, ladies and gentlemen. We're going to multiply that out. That's going to be 2, and that's going to be 1. So we're going to end up getting 16 minus 6y plus 6y equals 11. The 6y's cancel, and we end up with the wonderful truth, which you never knew before now, that 16 equals 11. Okay? Something went wrong, and if that happened to you in real life, the first thing you do is go back and double-check all your steps to make sure you didn't make a mistake. And we didn't. Okay? So the question is, what the heck went wrong, right? I thought this was a valid way to solve these algebra problems. My teacher taught me that in 9th grade or whatever. Here's the deal. That system of simultaneous equations has no solution. There is no way to get a value of x and y to satisfy both. And the reason you can see, if you look at these equations a little bit more carefully, so check this out. What I've said here was 2x plus 3y equals 8, right? Now, if you think about it, this next equation, 4x plus 6y, well, that's just twice this first one, right? If I take this first 2x plus 3y, whatever x and y are, and I double it, I'm going to get 4x plus 6y. And you can try that if you don't believe me. So let's say x is 2 and y is 1, just picking a couple values here, right? Well, 2 times 2 plus 3 times 1 is equal to 7. And sure enough, 4 times 2 plus 6 times 1 is equal to 14, right? So clearly, if this thing equals 7, then this thing's going to equal 14, because all we did was double the left-hand side. Obviously, we're going to double the right-hand side, right? So what this means is that if you're telling me 2 plus 3 equals 8, Jack, well, I can tell you right now, 4x plus y is going to be 16. It can't be anything else. It certainly can't be 11. You can't have 2x plus 3y equaling 8 at the same time you have 4x plus 6y equaling 11. Because 4x plus 6y has got to be double whatever 2x plus 3y is. Okay? Now, if you look at this a little bit more carefully and think about what we did at the very beginning of episode 3, you will also recognize another thing. Look at this for a minute. I don't even care about what's on the right-hand side of the equal sign for now, actually. I just want to look at these things. If you look at that and that, what do you see? The answer is you see blue dominoes. Those two vectors, if I make a vector 2, 4, or maybe I want to draw it like this, and you make the vector 3, 6, or maybe I want to draw it like this, we can see that one is a multiple of the other, right? If you take that guy and you multiply it by, I believe it's 1.5, you're going to get this guy. Or, if we think of it in terms of our Cartesian plane here, we can see that these dominoes are going in the same direction. 1, 2, 1, 2, 3, that is the vector 2, 3. And then 1, 2, 3, 4, 5, 6, that is the vector 3, 6. And they are right on top of each other. These are clearly not linearly independent, which means they're linearly dependent. And clearly they are blue dominoes, right? And those two concepts, the fact that the math broke when we tried to solve it using algebraic principles, and the fact that those two columns are not linearly independent, turn out to be exactly the same thing. Those are two different manifestations of the same phenomenon. And what that means is essentially that we've got a singular matrix on our hand. A singular matrix, okay? And we're going to talk for the rest of this segment about singular matrices. They are super important. They're rare in the sense that if you just give a random matrix, off the shelf at Walmart or whatever, it's going to be non-singular. But singular matrices come up enough, and it's certainly important to understand the theory, that it's going to turn out to be really important. Now, you may have been thinking when the algebra broke there, you may have been saying, well, we did that substitution rule that Mrs. Seastone taught me in whatever grade that was, and it didn't work out. It turned out that 11 was equal to 16, and so something broke. But you know what? Why don't I just use Stephen's cool shortcut that he taught us last segment, right? Because Stephen taught us that you don't even need to do any of that algebra. All you need to do is find that matrix, take the inverse, and then multiply it by the other side, and we're going to end up solving the problem. Let's just solve it that way, and then that way we'll get the answer, right? Well, let's see what happens when you do that. And actually, I'm just going to declare what happens because you're not going to realize this happens until we start doing this in a programming language and we actually get the bad news from R or Python. But remember that this is essentially what we boiled that down to, right? Our system of two equations, two unknowns, can be represented in matrix form this way. And remember, what we have to do to solve this thing is we have to multiply the left-hand side by the inverse of this matrix here, and multiply the right-hand side by the inverse of this matrix, and then this here will work out to be the identity matrix, and that multiplied by 8xy basically just goes away, and all we have is xy, and then we have the answer on the right-hand side, right? Okay, so why can't we solve it this way? And the answer is the matrix, in this case, is called a singular matrix, and what that means for us is it has no inverse. So remember, last segment I said, I'm kind of leaving open the question of, does every matrix have an inverse like this? Because all I did was tell you magically what it was, right? I didn't teach you how to compute it, and I'm not going to, because it's a pain in the butt and computers do it for us. So basically, I'm going to show you how to do it in R and in Python, and that's all you really need to know. No one computes the matrix inverse by hand, right? But if you have a singular matrix, it turns out that it has no inverse, and that's precisely why you can't cheat and use Stephen's little sexy shortcut to figure out the answer to your simultaneous equations if they have no solution, if they're blue dominoes, if they're singular, if they're messed up, because if you try to do it, boom, you can't get the inverse, and that is, fundamentally what the shortcut relies on, is the fact that you can take that inverse and get the identity matrix on the left-hand side. So all these ideas sort of go together, and this is what you want to get your head around, okay? If you have a matrix and it is singular, that means it represents a set of equations that you can't solve, and it means that you can't take the inverse. Both those two things go exactly together. Now, let me mention one thing when I talk about having no solution, right? So let's say I told you 2x plus 3y equals 8, and let's say I said 4x plus 6y equals freeze. Now I ask you, what can I finish that sentence with? What can I finish that equation with? Because there is an answer I could put there, right, which would give us a valid solution that can be solved, and that is the number 16. Because we know if 2x plus 3y equals 8, then 4x plus 6y has to equal 16. In fact, once I tell you that it's 16, I haven't really told you anything that I didn't already tell you with the first equation, right? Which is just like those blue dominoes. If I give you two blue dominoes, that means the second one didn't give you any information that you didn't already have in the first one, right? Similar to this here, if I fill in this blank with the number 16, then everything works and it's happy, sort of. And the reason it's only happy, sort of, is because this thing now has infinitely many solutions, right? In fact, if I tried to solve it using the same process I did before, right? If I say, well, I'm going to solve this thing for x, and I'm going to discover that x equals 8 minus 3y over 2, and then I'm going to substitute that x into this guy, and I'm going to end up getting, 4 times 8 minus 3y over 2 plus 6y equals 11, and then I multiply this thing out, and I say, okay, great, then we got 16 minus 3y, I'm sorry, minus 6y, oh, sorry, not 11, sorry, 16 here is our example we're doing right now. Minus 6y plus 6y equals 16. The 6y's cancel, and I end up with a wonderful piece of information that 16 equals 16. Now, no one's doubting 16 equals 16. I'm sure it is. The problem is that doesn't help at all, right, in finding a solution. And really what happened there is we have an under-constrained system is what it's called. And we'll talk about that a little bit more later. But the bottom line is really what we have is one equation, two variables. We have one equation, two unknowns. Even though I gave you two equations, I really only gave you one equation because the second one was a dupe of the first, right? The second one was just double what the first one is. So just like when I give you two blue dominoes and the second one doesn't give you anything more than the first one did, so if I give you both those equations, it doesn't shed any more light on what x and y's value are, which means as long as you satisfy the first equation, which you can with a lot of different numbers. In fact, let's do it. Let's just pick x equals 14. Sure, I like 14, except that's a big number. I shouldn't have picked that. Well, anyway, plug that in there, right? So let's say we have 2 times 14 plus 3y equals 8. Then 2 times 14 is 28 plus 3y equals 8. I'm going to subtract 28 from both sides, and I'm going to get 3y equals negative 20. I'm going to divide by both sides by 3, right? Negative 20 over 3. Okay, so what I've just proven is that x equals 14 together with y equals negative 20 thirds is a solution to this. However, there's infinitely many more solutions. If I just say x equals 1, plug that in. Okay, now we've got 2 times 1 plus 3 times y equals 8. So now we got 2 plus 3y equals 8. Subtract 2 from both sides, we get 3y equals 6. And now we divide both sides, y equals 2. Bada boom. Now x equals 1, y equals 2 is also a solution. And pick your favorite number for x and solve for y, and you've got another solution there too. So when I say that it corresponds to a system of equations that can't be solved, really what I mean is this. It can't be uniquely solved. It either can't be solved at all, because if I put any number other than 16 on the right-hand side of that second equation, we're toast. You can't solve it at all, right? We get some stupid thing like 11 equals 16, which obviously doesn't work. Or if I happen to put the one correct thing in there that will work, that's great and all, but I haven't given you enough information to figure out what x and y are because I haven't really given you a second equation in that case. I've only given you one equation. So, bottom line is, if you take the coefficients of your equation, you put them into a matrix, and you discover, I'm going to teach you how to discover in R and Python, and you discover that matrix is singular, then either that means you can't solve the thing at all, or it means that your right-hand side just happened to work out to where you can solve it infinitely different ways. Okay? So let's end this segment by tying together a number of different ideas, and I want you to understand this is really deep stuff. This is where it gets non-mechanical, this part of linear algebra, and it gets very, very deep. I want you to realize that all these things go together. If I have a non-singular square matrix, which again is the norm, okay, if you just pick a random matrix, it's going to be non-singular, just like if you pick random dominoes, they're going to be yellow. If I have a non-singular square matrix, that means, among other things, that all of its columns are linearly independent. You can't get any of them from any combination of the others. It also means that it is of full rank, because that's really what full rank means, right? If it's a 4 by 4 matrix, it has rank 4. There are a full set of linearly independent columns. That also means that the kernel of the matrix only has the 0 vector in it. The only way we can multiply that matrix by anything and get all zeros is if we multiply it by all zeros. The kernel, null space, whatever you want to call it, of A only has the 0 vector in it, which means the nullity of that matrix is 0. Which means, by the rank nullity theorem, that it has full rank and no nullity. And what I'm teaching you in this segment is that means it has an inverse. It is invertible is the word. And that means we are able to solve the simultaneous system of equations for which that matrix is an example, simply by multiplying both sides of that equation by the inverse. All those go together. And then on the flip side, here's your blue slide, right? That one was yellow, this one's blue. If A is singular, that means it's screwed up in some way. It means that its columns are not all linearly independent. You can make at least one of them from a combination of the others. It also means it's rank deficient. In fact, rank deficient means it doesn't have a full set of linearly independent columns. And therefore, the rank of, if it's 4 by 4, the rank is going to be less than 4, right? It also means that the kernel of it has more than just the 0 vector. There's a way, in fact, infinitely many ways, to get the 0 vector by multiplying that matrix times a lot of different vectors. It's no longer the case that you got to multiply by all zeros to get all zeros. Instead, you can multiply by a lot of different things in order to get all zeros, and the nullity of it is greater than 0 for exactly that reason. The nullity essentially means the dimension of the set of vectors that you can multiply it by and get 0. And that is no longer just the 0-dimensional 0 vector. Now it's going to be an entire line or an entire plane or an entire higher dimensional space. In this case, there is no inverse. In fact, another word for singular is non-invertible. And that corresponds to a system of equations which can't be solved. Or if it can be solved in infinitely many different ways, which is sort of the same as saying it can't be solved. You can never determine definitively what x and y are because there's infinitely many different solutions, or there's none at all.